Okay then. So to continue, we were finishing up, well, we have two more lectures to finish on principles of chromatography, and on Monday we'll cover the HPLC lecture, and then we'll move on to spectroscopy. So just to get you back to where we left off in terms of basic principles of chromatography, and like I mentioned earlier, my focus is liquid chromatography since you've already covered gas chromatography with Gary. So let's try to remember together a few things from past lectures and then continue from where we left off. So what is supercritical fluid chromatography? I will try to open my chat here to see what we get. If we get anything in the chat box, and also if anybody here wants to remember, Giorgino. Exactly. So it is the chromatography where we use a mobile phase that's originally gas, and we bring it to what would be liquid type of mobile phase by increasing the pressure and temperature above critical point. So CO2, for example, is one mobile phase that is used above the critical point for temperature and pressure, and therefore enhance the supercritical fluid chromatography, where we use same setup of HPLC unit, for example, but we use detectors that are common for GC detectors. What is reverse phase chromatography? Sam?
You have a polar solvent, or polar phase and non-polar.
Exactly. So in reverse phase, we have a non-polar stationary phase and a polar mobile phase. In this type of chromatography, which component elute first? The non-polar or the least polar, or the most polar leaves the column first? The most polar, Giorgino. Okay. So in reverse phase paper chromatography, what type of compounds travel the most with the mobile phase? We already said that. It's in same thing. The most or the least polar will be retained the most because they would like to associate via non-polar interaction with the stationary phase, and the most polar will move the most. Okay. How does thin layer chromatography differ from paper chromatography? What's the unique differences?
The silicone.
Cat. This is cat.
The silicone or other like substance that's put on the metal instead of just having paper.
Yeah. So how does that make it? Does it make it better for resolution, or that makes it better? It makes it better for resolution because then you have a better uniform particle size for your stationary phase and consistent in thickness. So you don't have differences like you would have in paper chromatography, and then you would have more reproducible results and better separation. So when we say isocratic versus gradient elution, what do we mean? Yes, Anastasia?
Isocratic just means there's one concentration, while gradient makes the mobile phase stronger.
Over time, yes. So isocratic elution, that means we're using one type of mobile phase and we don't change its concentration over time, so it's constant over time. Whereas with gradient, we start at a specific concentration and we increase the strength of the mobile phase over time. So we utilize different multiple solvents. What does increasing the strength of the mobile phase mean to you? When we say we're increasing the strength of the mobile phase, what does that mean? Yes, Jean? Exactly. So making the mobile phase more like the stationary phase, so that the constituents that are interacting with the stationary phase have more tendency to walk away with the mobile phase. So basically, increasing the strength can be in any form, depending on the mode of separation. If the mode of separation is reverse phase, increasing the strength is by adding organic solvent over time. If the mode of separation is normal phase, that means you are increasing the strength by adding water, for instance, or polar phase over time. So it doesn't always go in one direction. It depends on your stationary phase, and hence the mobile phase changes in that direction. Okay, good. So we were talking last time about, let's see, where am I? Okay. We were talking last time about different modes of separation, and one of it is adsorption chromatography. In adsorption chromatography, your components are adsorbing on your stationary phase. So the different components are adsorbing via different intermolecular interactions or forces. And these are all non-covalent. You do not want your components to covalently link to the mobile phase, and it's really tough to break these bonds and let them out. So we want to have interactions that are non-covalent, and most common interactions for adsorption chromatography are van der Waals, electrostatic, hydrogen bonding, and hydrophobic interactions. So your stationary phase, or we call it the adsorbent, where your components are going to adsorb to it, are usually finely divided solids. So there are particulates that are fine of very unified or very unified size. And then these solid particulate allows interaction of the components so that they get separated based on how much they have affinity to the color. So how well the interactions are with the cone. So the more you have interaction, the more the compounds are going to be detained on the cone. And the more you have differences in interactions, the more you're going to get separation between the components. In partition coefficient, we say partition coefficient is constant. Adsorption coefficient is not constant. So the difference here, you have a set amount of functional groups on your stationary phase. So depending on how much you have components, like these red triangles here, these are your functional groups on your stationary phase. So depending on the capacity of the stationary phase, your adsorption coefficient differs. And we will be talking about capacity on Friday. But sometimes you hear, I overloaded the column. So what does that mean, I overloaded the column? That means I injected more sample than the stationary phase functional group can withstand. So there will be more components and not enough room to interact on the cone. So concentration of how much I can inject is very, very important. Otherwise, I don't get clean separation. I might get the components coming out, the same component coming out with the mobile phase, with the front or solvent front, and interacting with the column, because I would have overloaded my capacity of the column, and I would have few compounds that don't interact. So I don't want that to happen. So the adsorption coefficient is related to the concentration that I am injecting, and also to the number of functional groups that are available for interaction. So the number of available functional groups depends on the size of the column. How big is your column and how much stationary phase you have in your column. And if your column is packed, that means that it's not a hollow capillary tube column, so it's packed. Or if it is hollow and it has a thin layer of coating, you have less capacity. So even if you have the same stationary phase and the same components, you don't have a constant because it depends on the capacity of the stationary phase and the concentration of your constituents. So keep that in mind. So in absorption chromatography, you can have a stationary phase made up of silica, alumina, or charcoal. So it basically, silica and alumina are polar, charcoal are non-polar. So if you have silica and ammonia, interaction is via polar interaction or kind of like normal phase separation. If you have charcoal, it will be based on non-polar interactions, so it would be reverse phase absorptive chromatography. But you can also have bonded silica. For the example, some of you did the HPLC lab. We had a bonded silica stationary phase where we had silica bonded to C18, for example. C18 is a chain of 18 carbons, so it's turning the stationary phase into nonpolar. So you can get the silica but bonded to different types of hydrocarbons, then you can have different hydrophilicity and hydrophobicity or polarity. So if you have bonded to C8 versus C18, or sometimes we have C30. So the longer the hydrocarbon, the more it is hydrophobic. So it would be less polar. So for C30, let's say we use C30 column to separate carotenoids. So carotenoids are more hydrophobic. So then we need a more hydrophobic stationary phase in order to separate them. C8 is less hydrophobic than C18, and C18 is less hydrophobic than C30. So basically, the elution order depends on the relative polarity of your components in this case. And the solute and the solvent, they compete to interact with the stationary phase. And we talked about changing the strength will alter the solute stationary phase interaction. Oftentimes, we use this strategy, which is the gradient elution, to reduce our analysis time. Because sometimes you have components that vary a lot in how much they interact with the column. Some components interact a little bit and come out fast. Other components interact very strongly and they will be delayed. Eventually they will leave the column, but it will take a really long time. So that's why increasing the strength helps in shortening the analysis time. Partition chromatography, we talked about it briefly earlier, where you have, is it hard for other people to hear? Let me see. Who asked this question? Can you type in if you can hear clearly? Say yes, or if you can hear me, please. Okay, good. I'm trying to be close to the computer as much as I can. Okay, try not to move. All right, partition chromatography, that means when I walk away. Okay, I'll try not to wander. All right, I'll try to stay by the computer. Okay, so liquid chromatography, here's where your stationary phase is liquid and your mobile phase is liquid. And so your components are separating between the mobile phase and the stationary phase based on their solubility. So hence the partition chromatography is the partitioning between one solvent and another solvent, and one of these solvents is bonded to an inert surface, and that makes it its stationary phase. So we have usually in partition chromatography, you have either normal phase or reverse phase mode of separation. Normal phase when you have a polar stationary phase and nonpolar mobile phase, and the opposite is true for reverse phase. So you can have either a coated support or a bonded support. That means you would have silica, and then if it is just coated, it becomes a silica gel, because then you have that liquid, which is, we call this hydrated silica, and usually your liquid is water. And or you can have cellulose or glass beads, and then you can have your stationary phase being a water or a nonpolar solvent. Bonded support is when you have a covalently bonded liquid phase to the inert surface. And the example of bonded is also silica. If we have silica gel, you can have it also bonded to a hydrocarbon. So a unique form of chromatographic interaction is hydrophobic interaction chromatography, which is also based on adsorption chromatography. So it's one form of adsorption chromatography, and it's very specific and mostly used in protein separations. So it is a very, very specific type of chromatography, and it requires the presence of salt. So usually you solubilize your sample that you're trying to separate in a salt solution. So if you have salt is going to block the charges on your samples, on your constituents. So proteins, for example, that's why it's very specific to proteins, because proteins have charges, and when you have high salt concentration, the charges are going to be blocked. So the protein hydrophobic surface becomes more active for interactions. So you would have a weak hydrophobic surface on the stationary phase, and then they would attract the hydrophobic surfaces of the protein once all the charges are shielded. So the biomolecules, mostly proteins, absorb by weak hydrophobic interactions in the presence of high salt concentration. So often your stationary phase is a hydrophilic support bonded to a hydrophobic ligand. A very common one that we use in the lab is butylcetherose. It's a very common hydrophobic interaction chromatography stationary phase. What is today, Wednesday? First Wednesday of the month? Okay, so that's what we're hearing. So the mobile phase here, we start with, like I said, the high concentration of salt, and oftentimes it's specifically ammonium sulfate, and 1 molar concentration is a common starting point concentration. So your sample is dissolved in 1 molar ammonium sulfate, and your mobile phase is 1 molar ammonium sulfate. So in this case, and then you decrease salt over time to get your components out of the column. So this is an illustration how that happens. When you have high salt concentration, and I will you point, I'm not gonna wonder, I'm gonna point with my mouse. So here you have your protein hydrophobic surface is interacting with hydrophobic ligand on the stationary phase, because you have high salt concentration, so the charges are shielded, so you have interaction going on. The most hydrophobic will interact the most with the column or with your stationary phase, and the least hydrophobic or protein has surfaces, right? And the surface on the protein can be very hydrophobic or moderately hydrophobic or mildly hydrophobic. So when you block all potential polarities, that means potential polar components that are your charges, when you block them with the salt, so now you kind of highlighting hydrophobic interaction. So those that are least hydrophobic will interact the least and will leave the column first. Those that have the most surface hydrophobicity, and when the charges are shielded on the same surface, then they interact the most with the column. And then we don't want them to stay interacting. So the way to increase the strength of the mobile phase in this case is reduce the salt concentration. So over time, you reduce the salt concentration. And when you reduce the salt content concentration, those that are least hydrophobic will move first. You'll separate them first, then the modest or moderate, then the most hydrophobic will come out. And thus you achieve separation. So as a recap, in hydrophobic interaction chromatography, interaction between the solute and the stationary phase are mostly what? What type of interaction? Hydrophobic interaction. Just simple. Yes, Sam?
Is it possible to flip it like the salt or something on polar and then have a polar stationary phase?
Then it will become hydrophilic interaction chromatography.
Okay, so that's still.
Yeah, yes. There is something called hydrophilic interaction chromatography. I talk about hydrophobic interaction chromatography here because it has more applications, mostly in the protein field. So the next one, the other mode of separation that is under another specific adsorption type chromatography is ion exchange. Again, you have adsorption going on, but it's very, very specific where you have electrostatic interactions. So you have these interactions that based on ion or charges. So in this case, what you have is you have a cross-linked resin. So your stationary phase is made out of molecules that are cross-linked together, and they have functional groups that carry charge. So usually before you inject the sample, you have your resin with its ligand here. Let's say it has a function group that is negatively charged. You do have a counter ion when the stationary phase is idle. So you have a positive charge counter ion. When you inject your sample, those samples that are positively charged are going to displace your counter ion and interact with the negatively charged functional groups on your stationary phase. Then the interaction is electrostatic. Positive is being attracted by the negative ions on your stationary phase. So your resin can be highly cross-linked. So this would make it have small pores, and these are usually you have more capacity when you have small pores. That means you have more functional groups that can be conjugated on the resin. That you can thus with when you have more functional groups, then you can have more capacity. That means you can have more components interacting with the column. So you enhance capacity and you enhance selectivity. And we'll talk more about capacity, selectivity, efficiency next lecture on Friday. When you have a lightly cross-linking, you have large pores. So this allows separation of larger molecules. So when you have larger molecules, you need larger spaces for them to come through and interact with your functional groups. So lightly crossed are usually used for large molecules such as proteins or nucleic acids. The highly crossed would potentially be for amino acids, for example, small groups, small phenolics, small charged organic acids, for example. So common resin is polystyrene divinyl benzene. So you have the styrene and divinyl benzene cross-linked together. And then you have here the R group, which can be derivatized with a positively charged functional group or a negatively charged functional group. So if it is positively charged functional group, it becomes an anion exchanger. Remember what we talked last time. Anion exchanger, the word means it's exchanging anions, negatively charged ions. In order to interact with negatively charged ion, that means it's carrying a positive charge. And when you have a negative charge stationary phase, it becomes a cation exchanger. It's exchanging cations, positively charged molecules. A very common stationary phase for ion exchange is a polysaccharide-based stationary phase. Polysaccharides with glucose units as subunits that are cross-linked. So here you have the OH groups are derivatized to give you negatively charged or positively charged functional groups. So these OH groups can be derivatized with a weak acid or a weak base. If they are derivatized with a weak acid, they carry a negative charge, but they can easily be protonated. What does that mean to us? This one can easily be protonated, and the weak base can easily be deprotonated. What does that mean? It means that if we change the pH of the mobile phase, these function groups will be impacted. So if I have a weak acid and I decrease the pH of my mobile phase, it's going to get protonated easily, and it will impact its interaction with the molecules, and the molecules are going to move out faster from my column, the molecules that are positively charged. If I have a weak base, and then I increase the pH, then they're going to lose their proton. They're going to be deprotonated easily. With that also helps with detaching the molecules that are interacting and letting them leave the stationary phase. So weak acids and weak bases are very much influenced by the pH of our mobile phase. So one of the ways to increase the strength of the mobile phase when we have weak acid or weak base is changing the pH. By changing the pH, I change the selectivity, and by changing the selectivity, I enhance my analysis time or reduce my analysis time. These same functional or OH groups can be derivatized by strong base or strong acid. In this case, the strong base is not impacted by pH change. So no matter how we change the pH, it will still carry a positive charge. And no matter how we change the pH for the strong acid, it will still carry its negative charge. So this one is not easily protonated, and this one is not easily deprotonated. In this case, we often run an isocratic separation. So here's just a little bit more explanation on the nature of the exchanger. When it's strong acid, it really negatively charged over a wide range of pH. Anything above pH 2, it's negatively charged. So that's when you really, it's not impacted by pH, you'd rather run isocratic separation. And when you have the strong base, it's also positively charged at any pH below 10. So it's a wide range of pH where it's not going to be impacted by any changes in pH. And then here, the weak cation exchanger, you can change the capacity a lot by changing the pH between 4 and 10. And then same with weak anion exchanger, that means a weak positively charged, it can get deprotonated in moderately basic conditions. So these two can really change in their protonation, based on the pH. So increasing the strength and decreasing the strength, well, increasing the strength, I would say it depends on the type of the stationary phase. Either you increase the pH or you decrease the pH. And there's a table that tells you when you would do that coming up later. Or another way of changing the strength of your mobile phase in ion exchange chromatography is increasing the salt concentration. So you can have a buffer running through your column at a particular pH. You can change the concentration. Let's say in your buffer you have NaCl, you can increase the concentration of NaCl. NaCl has a positive ions, Na and Cl minus. So whether you are doing anion exchange or cation exchange, doesn't matter. Increasing the salt concentration would reduce the interaction with the column because the salt ions are going to displace your components from the column and have them move along in the mobile phase. So the ions are interacting based on ionic valence, or how many charge groups are in your valence or the outer shell of your compound or molecule. And then the radius, how big the compound is, and the concentration. So these all impact how much they're going to interact with your column. But the ionic valence is the most important, because when you have, let's say, a compound with more positive charge, like a net positive charge of 10, let's say, versus a compound with a net positive charge of 3, and you have cation exchanger where you have negatively charged functional groups on your column, the compound that has the most net positive charge will interact the most. And the compound that has the least positive charge will interact the least. So the one that is least net positive charge will leave the column first in cation exchange chromatography. Okay. You can ask questions if you wanted me to repeat anything. I know this is the most confusing absorption chromatography is ion exchange chromatography. Okay. Yes, Al? Yes, exactly. So basically you choose anion or cation based on the components of your samples. Let's say in Agripore, for example, I got this question earlier in lab today. They separate whey protein and isolate whey protein, isolate using anion exchanger, because the whey protein at pH 7 is negatively charged. So they separate it from other components based on the charge of that protein. So when you have negatively charged components that you want to separate, you would use anion exchange in your mixture. Because if you have positive and negative, the positives are not going to interact and they're going to elute first and leave. They're not interacting with your column. The negatively charged components they're going to interact with the column. Now, the negatively charged components, if you decrease the pH over time during the elution, they're going to capture protons. So they're no longer negatively charged, so they move along your column. So when you change the pH, you change the ionization state of your components. Good. So in ion exchange chromatography, interaction between solute and stationary phase are mostly electrostatic. Just making sure that you are awake and you know what we're talking about. Great. So another form of absorption chromatography is affinity chromatography. Again, it is absorption, but this is very specific type of absorption chromatography where you have a very strong interaction, very specific interaction between your stationary phase and your components. This is used sometimes to purify, for example, antibodies from a mixture of antibodies. Let's say you've taken a serum from an animal and you want to specifically isolate a unique antibody that you would use in an assay, in an immunoassay. So one way to do that is to run it through an affinity chromatography. So you would have on the column, then in this particular case, you have an inert support, you have an arm of some form of organic compound that would bind to a ligand. The ligand in this case would be specific to the antibody that you are trying to separate. So this means the ligand is an antigen to this antibody with a specific epitope that would interact with the antibody that you want to separate. So then your antibody of interest will be the only one interacting with your ligand here. Sometimes you want to isolate enzyme inhibitors or enzymes. So you have a mixture of enzymes and you want to purify a specific enzyme. So you use your ligand in this case would be an enzyme inhibitor. So it will react with the enzyme via very specific interactions. And then other enzymes will elute, and then you would have your purified enzymes. Sometimes you are using a general ligand. Lectins, these are ligands that can separate glycated proteins, for example. Any protein that is glycated can be separated by this general ligand here. So your stationary phase would have a high surface area so that you can have many ligands attached to it, so you can increase the capacity. It's porous to allow space for large molecules, does not absorb anything, so it's inert. And what we choose usually for this is agarose, cellulose, dextrin, polyacrylamide, or glass, where we attach our ligand to. So they're inert, they don't interact with your sample. That's what you want to interact with your sample is your particular ligand. So you achieved an interaction. You specifically have a ligand for your target. Now everything else leaves the column that is not specific, because here the interactions are very, very unique, like lock and key. So everything else will just leave the column. Now, but you want your sample to come out. You want your component to come out. How do you make it come out? There are two ways: non-specific and biospecific. Non-specific meaning, the interaction is very unique. If I change the pH, I'm changing the ionization state. If I change the salt, the same thing. That means I'm going to disrupt some of the interactions. Once I change the conditions, I'm disrupting the interaction. The molecule is going to leave the column. Another way to do that is use a biospecific way of separating or eluting. And that means you see this ligand here, I can introduce this ligand that is attached to your stationary phase. I can introduce the same ligand in my mobile phase. So if I have an enzyme inhibitor, or I have an antigen specific to antibody, I can have that same ligand in my mobile phase. So, and then I introduce that into the system, then my sample or analyte would start interacting with the ligand in the mobile phase and then moves along and leaves the column or leaves the stationary phase. Okay. So in affinity chromatography, interactions between solute and stationary phase are mostly what in this case? Yes, I would repeat the question. Okay, so what would it be in this case? C? It will be C, but only C? C, D, E, B, A, all of them. So you can have all or some of them depending on the molecule and the stationary phase. So any specific interaction can involve any of these interactions, sometimes multiple or all of them. Okay, so size exclusion chromatography is a chromatography that is separate, different than absorption chromatography or partition chromatography. It's its own unit, and it's only based on the size of the molecule. It's not based on any physical chemical characteristic or chemical characteristics. It's based on the size. So large molecules travel with the mobile phase and it goes out in what we call the void volume. So that means the large molecules, they don't have space to go into any of the pore sizes. So you have particles, so your column is packed with a certain material made up of uniform particles. Each particle has pores. And sometimes you have a range of sizes of pores, especially if you're trying to separate compounds with different sizes. So you have large pores, medium pores, small pores. But a very large molecule usually does not go in any of these pores. A very large molecule is just going to go around the particles. So in the spaces around the particles, move down the column and go out with what we call the void column volume. So the void column volume, we often measure it by blue dextrin, for example. So if I want to know how much is my void volume, which I needed in certain calculations, I would run a very large molecule through my column and determine at what time and how much volume it took for that very large molecule to come up. Blue dextrin is what we usually use, and it's blue because we can measure the absorption and determine when it comes out. So, and then we know how much is our void volume. So, on the contrary, components that are very, very small, so like these pink ones here, they're the smallest. So they're going to go, they have access to all the pores. So they have access to the small pores, to the large pores, so they're going to go in and then they're going to get detained in the column because they're going to go into the pores and then come out and then go into other pores. So they will take the longest time to leave the column. And there's nothing much you can do about that. So it's nothing that you can do to increase the strength of your mobile phase. Usually you run isochromatic and size exclusion chromatography. So depending on the size then, the largest come out first and the smallest comes out last. So here's more illustration of the smallest going into the different pores. And like I said, you have kind of a gradient of pores. You have pores of different sizes so that you can separate molecules of different sizes. So the smallest one have access to all the pores and the largest one do not have access to any of the pores. So they get separated that way. So in order to determine, to run this and determine the molecular weight, sometimes you do size exclusion, not only to separate and collect fraction based on their size, but sometimes you want to actually determine the molecular weight of your sample. And this is the perfect chromatographic technique that will allow you to estimate the molecular weight of your compound. And sometimes you want to determine the impact of processing on changes in molecular weight. And that's very important in the protein research field. When you process and you form dimers or even larger polymers, so you want to know what happened and how that molecular weight shifted. So in order to determine that and assess the molecular weight, you want to run standard and then you run your sample. So when you run your sample, you want to determine what we call a certain constant. That constant is based on, let me see here, where am I? So you want to know your void volume, and you want to know your total volume, and then you want to know your elution volume for a specific component. That means how much volume it took to elute your component of interest. Your void volume is all the volume that is around the particles. And then the total volume is the inner volume and the outside volume. So it's the entire volume from beginning to end. So this you determine with the smallest molecule possible, and the void volume you determine with the largest molecule possible. So you get the smallest, you get the void volume, you get the total permeation volume, and you get the internal pore volume. So these are essential measurements you would need to determine the partition coefficient in this case, which is your constant. So you, like I said, you want to run standards of known molecular weights. So you would run these standards, and then you would determine the partition coefficient here, where it is your volume of elution for each of these standards or your sample component, minus your void volume. So you would know that by running a very large molecule, and you get your total volume of the interior and the exterior of your particles. And then you correct for the void volume in both cases. Then you get that coefficient, you plot it across log molecular weight. You would have your standard curve basically, and then you can calculate the molecular weight of your unknown by getting this K, or the partition coefficient of your unknown, and plug it into the equation to get your log molecular weight, and then you convert to molecular weight. Blue dextrin is used for mobile phase. What I meant is by blue dextrin, the mobile phase is usually either water or buffer, depending on your sample. The blue dextrin is a component you inject to determine the void volume. It's a large molecule you inject onto the column. It will not go into any pores. It will come out, and using the time it came out and the volume it took to come out, you get your void volume. So in size exclusion chromatography, what kind of interactions we get between solute and stationary phase? Ewan, none. Coleman, none. Yes, no interactions. So this type of chromatography, we do not have interaction. We have physical separation. So hence the name gel permeation is something is common. It means the same thing as size exclusion. So basically you have your gel that is made up of different pores, and your samples are separating physically based on their size. So there is no interaction with your stationary phase. So here's a very important table. So we're at the end of today's very good timing. This table here, let me close this chat box now. This is a table you'll find in your chapter, in your chromatography chapter in the textbook. This table, actually, I prepared it and added it to the new edition of the textbook because it summarizes everything very nicely in a way is what do I want you to know? It's right there. So if you want to study different modes of separation, this is the perfect summary table to do so. So you would have the different modes of separation. So separation modes, what would be your stationary phase? What would be the mobile phase? How would you increase your strength of the mobile phase in each case? What elutes first? And what type of interaction? You study this, your goal. Because a lot of the questions that I ask in quizzes and exam around chromatography is really in this table. If you understand this table, know this table, you're good. Okay, so this is how I'm going to end today. Any questions? All right, good.
Okay.
Yeah.
So Chris asked me privately, and I just responded. Oh, you just responded?
I responded to this. I told that reduction is not an amino acid, it's injected.
Okay.
I saw the question